Hi, welcome back. In our previous lesson, we looked at consumer optimization where we focused on utility. Today, we'll be looking at algebraic approach to the consumer choice theory we've been discussing so far. So we saw in our previous lessons that for each consumer, we can define a utility function as the formula that attaches a total utility value to each bundle. Let's look at a typical example for this. Let's consider a consumer named Ella who consumes two good X and good Y. So Ella's utility function, which is U as a function of good X and good Y, can be represented as this. Ella also consumes 4 units of good X and 9 units of good Y. So given this information, we can calculate Ella's total utility. So we know Ls utility function is represented as x raised to the power 0.5 and y raised to the power 0.5. Given the quantities of x and y that Ella consumes, Ls total utility is therefore 4 units of good x raised to the power 0.5 and 9 units of good y raised to the power 0.5. So this is simply 2 multiplied by 3, which gives us a utility of 6. What we are showing here is given Ls utility function as x raised to the power 0.5, y raised to the power 0.5. If Ella consumes 4 units of good x and 9 units of good y, her total utility is going to be 6. Now, using calculus, we can then move on to the marginal utility. So the marginal utility of a commodity given some bundle is defined as the partial derivative of the utility function with respect to the amount of that good. So what this reflects is how the consumer's total utility changes as the amount of the commodity is increased by a small amount, holding constant the amount consumed of the other good. So for Ella, her marginal utility of good X is simply the differentiation of the total utility with respect to good X. So what this function is telling us is how much does the total utility change when we change good X. Our utility function is given to us as x raised to the power 0.5, y raised to the power 0.5. Now, if we differentiate this function with respect to x, what we're going to get is 0.5x minus 0.5 y raised to the power 0.5. So this function here is the marginal utility of good x. Now, if we do the same for good y, the marginal utility of good y is simply the differentiation of the total utility function with respect to good y, telling us how much total utility change when we change y. So differentiating the total utility function with respect to y is 0.5 x raised to the power 0.5 y raised to the power minus 0.5. In our previous lessons, we defined the marginal rate of substitution, which is the slope of the indifference curve, as the ratio of the two marginal utilities. So let's now move on to show this mathematically. We first note that if we have a utility function represented by this, then the change in total utility by a small change in x and y is change in u being equal to the change in x and then the change in y. So as we move along a given indifference curve, the change in utility is 0. Now we mentioned this in our previous lesson, and this is because on any indifference curve, the utility is constant. So if you have an indifference curve like u1, and you have a point A which has this amount of good X and this amount of good Y, if you increase consumption of good X to this amount and decrease the consumption of good Y, which moves you from point A to point B, now there is a change in good Y and good X as we move from point A to point B. But this change does not affect total utility because we are on the same indifference curve. So this is the same as writing the change in U being equal to 0. So we can rewrite our equation here as mux dx plus muy dy being equal to 0. So we have rearranged the consumption of good X and good Y along the indifference curve, but that has not changed the utility. So the change is 0. Now let's move further to rewrite this function. So we can rewrite this again as mux dx being equal to minus muy dy. And again, we can rewrite this as mux divided by muy being equal to minus dy over dx. Now, this simply represents the negative of the slope of the indifference curve, which is the marginal rate of substitution. We know from our previous lesson that the ratio of the two marginal utilities is equal to the marginal rate of substitution. So if we rewrite this, we have marginal rate of substitution being equal to marginal utility of x over marginal utility of y. And this is what we have shown mathematically here. So we are going to use this information and this equation to solve the example that we have above. In our example, marginal utility of good x was given as 0.5 x minus 0.5 y 0.5, and marginal utility of y we found as 0.5 x 0.5 y minus 0.5. Now, these two can cancel, and our equation now becomes x minus 0.5 y 0.5 divided by x 0.5 y minus 0.5. Now, this can be rewritten as y 0.5 multiplied by y 0.5 divided by x 0.5 multiplied by x 0.5, and further simplified to be y 0.5 plus 0.5 divided by x 0.5 plus 0.5. And then our final answer is going to be y divided by x. So what we have shown here is, given our utility function as x raised to the power 0.5 multiplied by y raised to the power 0.5, our marginal rate of substitution, which is the slope of the indifference curve and can also be written as the ratio of the two marginal utility, is y over x. So this y over x, it shows the rate at which the consumer trades off between the two goods. So this is all that we have on our lesson on the algebraic approach to consumer optimization. Now we'll move on in our next lesson to the Lagrange method for finding the consumer's equilibrium. If you enjoyed today's lesson, consider subscribing. Thank you.